Today we're going to ask, can you use a vision language model to identify someone through a framework we call identity extraction? We're going to study the CLIP foundational model, which is trained on a huge corpus of public web data. Now, CLIP is important because it's fed into a variety of downstream systems such as image generation or language modeling. We want CLIP to have diverse knowledge of objects or places, but unfortunately these datasets have a huge subset of people and their names. So we envision a scenario where a user can learn somebody's name by submitting an image to CLIP. Now, once CLIP has knowledge of someone, that knowledge bleeds into all these downstream systems. So you could, for instance, use this person's name to maybe generate an image of them. We're going to ask two main questions in this work. The first one builds off previous research, which asks, does CLIP know my face? Now, this is useful in an auditing scenario where a model provider may claim that they have privacy in mind or that they did not train on your data, and you can use this framework to verify that claim. The second question we ask is, how many faces does CLIP know, or who is this person? This is a new setting where an attacker who does not have the ground truth name can actually extract that name from the model. The attack works like this. We have Bob here, who has a number of images of himself, and submits it alongside the Cartesian product of all these names on the right. Now, these bold lines here represent the argmax over the CLIP score. So this is CLIP's maximum choice. What he's going to do is count up how many times his images map to the correct name. And he's going to form his attack function, which in this case is 2. Now, he's going to deliberately submit incorrect names to give confidence on this number here. So the more incorrect names we submit, the less likely it is that we map to the correct name. In a harder setting, we have Alice, who has a number of images of Bob, and also a phone book where she knows Bob's name is inside, she just doesn't know which one it is. So she's going to do the same thing, except her attack function is now going to be the maximum frequency. If this maximum frequency is high enough, she's going to conclude this person is probably Bob Jones. But she's also learned that CLIP was probably trained on this person. In an even harder setting, we're going to assume that she does not necessarily have the ground truth name. And what she'll do is use the visual information from these images to generate names. So she'll generate her candidate set and do the same thing and take the maximum frequency. Now, in this case, distractors are very important. In the case when she does not generate the ground truth name, the model will map randomly to this set of distractors. We're going to generate names through reinforce. We're going to take a off-the-shelf language model like Mistral. We're going to generate some captions from the model, and then we're going to reinforce the model between those captions and the images. So as optimization goes on, the model generates more and more relevant captions. We're also going to propose just plugging in X to a off-the-shelf vision language model and then performing this extraction by selection attack. Our datasets are 10,000 people from VGG Phase 2 and 1 million names from Wikipedia as our distractor name set. The models under attack are those from a suite of models from OpenClip, which were trained on Lamb 5 billion, and also a data comp. What we're going to look at here is the second column. This is how many people we can extract at a certain precision. This means 99% of the time, our attack spits out the correct name up to a few characters. In the best case, we can extract 30% of the people from this data set, so that's around 33,000 people. If we relax this a bit, we can extract about half the people. Let's zoom in on this data comp model. Now, this model is interesting because the model creators had privacy in mind, so they blurred faces before training to prevent identification. Now, to be certain that the model is not using background information, which was not blurred, in its decision, we're going to do a strict facial crop here, which is shown in this second column here. You can see we can still extract 25% of the people. Now, to be absolutely certain, we also blur this strict facial crop, and we see that the attack performance goes to near 0. So this shows that either the blurring was insufficient or it wasn't done on all of the faces, but either way, this is a strong use case of this framework to show that you can audit a privacy claim. I'm just going to show some examples of reinforced working. So I'm going to start by prompting Mistral with pictured, and I'm going to generate a huge batch of different captions. And I take the clip scores with all those captions with our target person, Marvi Memon, who is a Pakistani politician. First we get relatively random captions, and then we get increasingly relevant captions until finally we generate the correct person. Now, a priori, we don't know which name is correct, so we'll strip all these names from all these candidate captions and then perform our selection attack on this candidate set. So in this work, we looked at two perspectives. The first is an auditing perspective, where we showed one use case against a real model data comp. The second perspective was privacy. We introduced a new attack which can extract names which were previously unknown just using images. In the future, perhaps we can use machine learning to unlearn these names from the model or train from the get-go with differential privacy. Thank you.